Okay, so this is a segment I like to call Sounding Smart. And as I've said before, that's important, more important than it should be. So here are two things that came up a lot on the test that you should be aware of. So the first one is a truss. When I asked what a truss was in that problem, everybody who made this mistake, I gave credit because everyone was doing it. But the truss is the whole collection of members, and a lot of people wrote the answer like it was a single member. So so the truss is actually, like this thing is a truss, and then the pieces or bars or beams or whatever. So the truss is the collection of bodies. Most people got the thing right where each of the members does have to be a two-force body, so you have to ignore the weight and all that kind of stuff. The loads need to act at the joints, but the truss itself is the collection. Okay, and then the second one was a lot of people in the question on the quiz asking why can't a truss have a fixed joint? A lot of people said because fixed joints provide a third force that's a couple. And so I just want to point out that a couple, since you're thinking of it as a pure moment, that's not really a force. I mean, I guess it's a pair of forces, but they cancel out as a force. It's a moment, and a moment is a type of load, but not a type of force. So loads are the big category that contain forces and moments. Okay. All right. And then, yes?
Just out of curiosity, are there other kinds of loads as well?
Those are the only two, I think. Yes. Yes. And then there were two other things that came up more than once. They're easy things to correct, but people were doing, oh, that's the end of this segment. That concludes Sounding Smart. Then there are still people who, when you know a force direction, are writing the variable associated with this as if it was a vector. So in a free body diagram, writing something like this, So don't do that, because you want to make it clear to yourself and whoever's looking at this that this force only has a single variable associated with it. And so that means if this is a scalar variable, you don't want any of that. You don't want the subscript notation or the vector symbol over it. Just write a scalar. I don't think I described why you don't want to use the subscript notation for scalar variables. And here's why. So if you have, okay, so let's say that there are these two members, and you're applying a force this way. This is member one and this is member two. And draw free body diagrams of both of these. So member one has this force, whatever it is, call it F. and then some stuff going horizontal that we don't care about. And then over here, we know the direction of this force. So let's say it's like this, okay? And what if you made the horrible mistake of writing this as the force on 1/2? Okay. And now you go over to this one. What are the forces on 2? Well, the only force horizontally, unless, assuming there's no friction, is a force that we know is pushing it that way. And using the subscript notation, this force would be the force on 2/1. Okay. So now say that you calculate one of these two forces. Say that for this, you get 50 newtons. Okay. That then, because this is the way the subscript notation works, it's very easy to make the mistake then of saying, well, then obviously F21 is -50, but a -50 Newton force in this direction is actually this way, and so it switches. Yeah, you get that double negative thing, and it messes up your signs. And if you're doing a problem where you don't have good intuition about everything that's going on, this will mess everything up, Yep.
Writing those with the arrow above them, doesn't that completely contradict?
Yes, so I'm doing this like some idiot might do. Yeah, so don't do this. Okay.
But still with the arrow above,
Yeah, don't do any of that. Don't do anything I just did here. Yeah. So instead, your free body diagram of 1 should be F and something else, F2 or R or whatever. Your free body diagram of 2 is just R this way. And then since these are scalars, the way Newton's third law works with these is you have the same variable, just in opposite directions. I'm sorry to anyone I called an idiot indirectly there. Yeah. Yeah, I would have known who if anyone would have just run out the door in tears. Any questions about that? So if you know the direction of a force, make sure that it's clear that that variable is a scalar. Okay. And then, yep.
When you calculate the number of crosses, so we include weight and mass of the members or neglect?
Yes, you do include them in the problems on the exam. Yeah, unless it says, well, generally, if you know the masses and you're trying to be as accurate as possible, then you might as well put them in. There are some cases where the other external loads on the members are so big that the weights don't change your answer noticeably. But in this class, in general, if you're given a mass, then include the weight. And then the next thing is that practice problem
number 1 is the
on internal loads.
we're mostly just trying to understand how you get the magnitude of the distributed load on the second.
Okay. I know. Well, let's just do the second cut. So this is number 1B. It's the one where you have a cantilever beam and a distributed load over half of the beam. And then at a 45-degree angle, you have a 25,000 Newton load. So as a vector, that gives you negative 17,677. No, positive x. And then negative 17,677. And on this one, you're not given a mass, so I guess we're neglecting the mass on this one. And this distance is 0.5 meter, and this is 0.5 meter. So the important points are here, here, and here. The one in the middle is because that's where the distributed load function changes. And in cut 2, we're dealing with x values in the region between 0.5 and 1. So our free body has the forces at the left, 17,677, negative 17,677. And then some amount of this distributed load. The magnitude of this, by the way, is 25,000 newtons per meter. And then we have the internal loads. Okay, so we need to come up with an expression for this width. You know, how much of that distributed load do we have for a given value of x? Right, so this should be x minus 0.5. Okay. And so now we can use that to rewrite the free body diagram with this distributed load represented as a point force. So it's going to be acting downward. The total force is the area of this rectangular shape. So 25,000 times x minus 0.5, or 25,000 minus 12,500. Yeah. 25,000 x minus 12,500. That's the magnitude of that force. And then we have the internal loads. And the other thing we have to figure out is the location of this force, because that's going to affect the moment it produces. So what's this distance?
X minus 0.4 over 2 plus 0.55.
That's right. And the way I like to think about it, to me, this makes sense. If you can come up with a way you like thinking about it better, go ahead. But we're going to take the midpoint between this and this. That's where we know the centroid is. This is at 0.5. This is at x. So we just need the average of 0.5 and x. So this distance is going to be x plus 0.5 over 2, or 0.5 x plus 0.25. And so then go to Newton's second law. This should be negative. So positive 17,677, negative 17,677, plus 0. Okay, so now you have to be careful with these signs. This is a downward force with this magnitude. So in other words, the vector is 0 and then 12,500 minus 25,000 x. You can think of it as it's this magnitude times a unit vector in the direction 0, -1. And if you multiply that, this is what you get. Then you have t negative v is equal to 0. So t is equal to negative 17,677, and v is equal to negative 5,177. Minus 25,000 x.
So can you look at your solution?
And acknowledge that it was wrong
Or just
in front of
like-
everybody.
Well, no, it was just either I'm wrong
Yeah.
or you're wrong, and I just want to know.
So, okay, the total magnitude of the force the total force is wrong.
Yeah.
Okay, and then
That point that it acts next to the 25,000. It looks like.
yeah, so my solution has 20, the downward force is 25,000 times the average of x and 0.5. So that doesn't make any sense there. So yeah, my solution is wrong for cut 2. Sorry about that. All right, well, so then you'd use this moment arm. We probably don't want to go through all the algebra because it looks like it gets sort of messy there, but this is the force that it should be applying. That's the point force. Anybody have any other questions about practice problems? All right, so today we're going on to how to calculate internal loads and structures. And I want you to, so here's what's different. So internal loads and structures. So here's what changes. Say that you have a structure like this. Some loads acting. And when you calculate the external loads on this, so you solve the structure, and let's say this is member 1. So solve the structure. And it tells you that your free body diagram of member 1 looks like this. You have a force vector here that now you know values for. So call that FA. You have a force vector here that now you have values for. Say let's just call that FB. And then you have this external force R. And you have one more thing going on. Let me move R over actually to this side. You have the weight of the member too, and that's a distributed load. And what direction is the weight acting as a distributed load? Yeah, the weight's always down. So you end up with something like this, right? So far, everything, we understand how to deal with all that. But now, we want to express all of these external loads in a coordinate system with the x-axis along the beam's axis. So notice, like all the internal loads problems we've done, we've had those beams lying flat down on the ground. And mathematically what that means is our x-axis is always pointing straight along the long axis of the beam. So we want to go from an original coordinate system like this to a new coordinate system like this. Okay, we want to re-express all of those loads. And if you do that, and I'll talk about how to do that, and it involves the rotation matrix that I brought up once before. But if you do that intuitively, you understand that you get this new, so you get this new set of loads. I'll call this lowercase fa, because it's still the same force, but numerically it's different. You have R this way. You have FB here. And what do you have for the distributed load? Well, it's not acting straight down anymore. Now it's acting, you can think of it as you have this distributed load that's angled in this direction. This is the distributed load. So the distributed load is now a vector with x and y components. Okay, so I'm going to start by just talking about how to deal with horizontal components of a distributed load. Mathematically, it's easy. And then I'll talk about how to go from the external loads that from some structure that you've solved to setting up an internal loads problem with these different components of distributed load. Okay, so we're going to be dealing with horizontal distributed loads. And the good news is we're only going to be dealing with rectangular horizontal distributed load components. And why is that? No, that's a good answer though, but no, that's not why. Another good wrong answer would be it's the easiest one, so maybe we just want to, you have to start somewhere. But that's not why either. The reason we're doing rectangular is because that's what represents weight. And weight is the big distributed load that comes up. I mean, weight comes up as a distributed load in every internal loads problem, unless it happens to just, it's in there. It's just some problems it doesn't make much of a difference, but it's always there. So we're gonna just learn how to deal with the weight of these members. Okay, so say that you have a cantilever beam coming out of the wall. Why do I keep doing these cantilevers with the connection at the right side? Yeah, because then we don't have to, then we can do the problem, do the cuts without calculating the external loads. So let's say that we have a beam, it's 2 meters long. And let's say that there is a horizontal distributed load going this way of 4,000 newtons per meter, and a vertical distributed load going down of 3,000 newtons per meter. What are the external loads? Well, the free body diagram has these distributed loads. And some things going on over here that we don't care about. We don't need to know those. Now that we've chosen, well, we haven't chosen a body to isolate yet, so let's do that. So this is a free body diagram of the whole thing. So now let's go to, so we have an important point here, an important point here. Nothing in the middle because those distributed loads are the same function the whole way. So that means we only have one cut. So our first cut is valid for all x values between 0 and 2. And a representative free body is like this, where the total length is x. We know that we have the internal loads. And now that we've chosen the body to isolate, we've chosen this chunk that's x meters long, we can represent the distributed load as a point force without changing the problem. So how are we going to represent these two rectangular distributed load components? Well, we know the vertical one. We've done that plenty of times before. So that's just going to be a downward force of 3,000 x. What about the horizontal force? Well, since it's rectangular, the horizontal force is just going to be 4,000 x pointing to the right. We have one more thing we have to think about. We went through all these calculations of how to figure out where the centroid was for vertical distributed loads. So where are we going to place this point force for the horizontal distributed load? Don't answer. What? Perpendicular, yep. So, and just write down the middle. So that is the way to do it, as long as we're dealing with a weight force. You could also have distributed loads that were produced by friction along the surface, and then that force would actually be located a little higher above the surface. And that stuff matters a little bit because the vertical position of this determines how big the moment arm is. And that determines how much of a factor it is in your rotational equation. But you don't have to think about that if you don't want, because for us, it's always going to be weight. That's always what's going to be producing this horizontal distributed load. And that always acts right down the middle of this member. And what about the horizontal position? It doesn't matter because of the line of action. That's exactly right. So we're going to put it just right along the long axis of the beam. And it has a value of 4,000 x. So now you can go to Newton's second law. That says, you know, you can write this as a single vector. So 4,000 x negative 3,000 x plus t negative v is equal to zeros. So t is equal to negative 4,000 x, and v is equal to negative 3,000 x. And now we'll go to the rotational equation. So what produce moments? Our about point is here. Does this horizontal distributed load produce any moment? No. If this is a thin beam and that horizontal distributed load was actually friction, would it produce a moment? It would, but it would be a small one if it was thin, because that moment arm would be really small compared to the moment arms of these length values, you know? So anyways, we don't have one due to the 4,000x. We still have one due to the 3,000x, just like we did in the last section of problems. What's the moment arm of this? X over 2, and is it clockwise or counterclockwise? Yep, so we got negative 3,000x times x over 2 plus m minus vx equal to 0. So m is equal to 1,500 x squared minus 3,000 x squared. So I just substituted in v. And you get a value of negative 1,500 x squared. And does the derivative condition hold? dm dx is equal to v, so yeah, that works. And so what we have here that we haven't seen yet, we've seen cases where the shear force is a, is a continuous function of x, but we haven't seen one where the tension was a continuous function of x. That's what this is going to give us now sometimes. Okay. Any questions about that one? So now I started out with like a simple problem with horizontal distributed loads where I just gave you the distributed loads. Now I'm going to do a simple problem, but instead of starting with this kind of coming out of the blue, we're going to develop like where that horizontal distributed load comes from. So think about this problem. What if you had a pin joint holding a long column up? And let's say that this has a mass of 500 kilograms, 5,000 kilograms. That's big. And it's 3 meters long. Well, what's your intuition about the internal loads on this? Where are we going to have the biggest value of internal tension? The bottom isn't going to have much because like a piece on the bottom right here doesn't have very much to hold up, you know. The top is going to have a lot. And so if you made something like this out of Play-Doh or something, you know, silly putty, you'd get a lot of deformation up near the top because this is the part, you know. Or like if this was a chain of people holding each other's ankles, and you know, like, would you volunteer to be this guy or this guy? You know, this guy has to hold up 50 people. This guy just has to hold on to the ankles above, you know. And what about shear force? Any shear force? Nope, no shear force. And any bending moment? Nope. All right, so first we have to calculate the external loads. This is a pin joint, so, and actually let's just skip all the, we know that everything's acting just straight up and down, so let's just think of this as a force with a known direction. We have that, and then we have a weight force of 5,000 times 9.81, so 49,050 newtons. So Newton's second law says 0R plus 0 negative 49,050 is equal to zeros. So R is equal to positive 49,050 newtons. So our final drawing of all the external loads is we have a distributed load due to the weight. And what's the magnitude of the distributed load? Or how do we get that? It's 49,050 divided by 3. So we have a total magnitude of 16,350 newtons per meter. And then we have an upward force of 49,050. And this is well, let's see. So now let's just say what?
Why would it be on the side of it?
It's not. It's right down the middle. It's just easier to draw it on the side. Yeah, it's right down the middle between the pins along the long axis. And so what if now we want to imagine it with a coordinate system like this, with the x-axis along the long axis and the y-axis this way. And why do we even want to do that to calculate the internal loads? Why do we care about the orientation?
Well, we can make it a point force along the x-axis.
Yeah, I mean, it's like we want that tension because of the way that we're used to doing these internal load problems. We always want tension to be along the x-axis, shear force to be along the y-axis. And so I'm just going to take this now and just sort of mentally redraw everything. So if I'm looking at it from this side, here's me. Okay. So that 49,050 newtons is pointing into my eye. So that's over, well, that's not really how I want to look at it. No, don't do that. We want to look at it like this. Yeah, we want to, that's the back of our head. You know it's the back because that's your butt. Okay, so we want to look at it like that. Okay, so the arrow is pointing to the left. The distributed load is pointing to the right. Yeah, because really it's acting right down the middle. Yeah, it doesn't matter. Right, right. And then there are no forces here. And now that we have this oriented the right way, how many cuts do we have to make? Just one cut. There's an important point there, an important point there. So, whoops. So we have a single cut. That's valid for the whole interval from 0 to 3. Well, you can put your coordinate system however you want it, and mine is like this. Yep.
So would you, maybe this is sort of, I can't remember, why were you ignoring the R?
We're not, it's right there. We calculated it. So in our cut, we have that 49,050. And we have the distributed load of 16,350. And we have the internal loads. And the length is x. And now that we've isolated the body, we can treat that distributed load as a point force. So we have 49,050 this way. And what's the magnitude of the point force caused by the distributed load? That's right, 16,350 x. And then the internal loads, T, V, and M. And now Newton's second law says 49,050, negative 49,050, 0, plus positive 16,350 x, 0, plus t negative v is equal to zeros. That tells us that the tension is equal to 49,050 minus 16,350 x. The shear force is 0. And now we'll go to the rotational equation. Do either of these two forces produce moments? Nope. So all that we have is m minus vx is equal to 0. So m is equal to vx, which is 0. So we get no shear force, no bending moment. And if you plot out the tension as you go from 0 to 3 meters, you start out at positive 49,050 and go linearly down to 0. So this is the internal tension close to that pin. And as you get farther and farther towards the other end, you drop down to a tension of 0. And notice that, well, you know, because of the sign convention of internal tension, a positive value means this is an internal load that is stretching the object. If you get one of these and get a negative value for the internal tension, it means it's compressive and the thing is being, you know, pushed together. Any questions about that? Okay, so, oh yeah.
Can we say, so the derivative of momentum is shear force,
Right.
but when we say the total area, the shear force can be the momentum.
Yes, but there's a constant of integration in there that you can't find unless you do the physics of it. So yes, you're right. All right, so notice that this problem, so really this is the whole idea, but it's a simple problem because when you do rotations of 90 degrees in your head, it's pretty easy, you know. What if you had to rotate one of these, the coordinate system, 37.5 degrees? It'd be a lot trickier to re-express all of your force vectors and things and distributed loads into that new coordinate system. And so when we come back from break, I'll talk about the rotation matrix, and then that's what we're going to use to transpose these forces and things into our new coordinate system. Okay, so I guess come back at 2:10.